we talked about matrices and linear transformations, I think. Yeah, I'm pretty sure that's the last video I can check before I recorded this video. So today we're going to be talking about vectors, and the concept of a vector is going to be very, very important in a majority of the courses that I'm going to be teaching at the Lyceum of St. Candice. Um, and the concept of vectors, sort of encoding characteristics or things that we're going to describe human beings for, is a very crucial concept in our curriculum. And well, first and foremost, give you guys sort of the layout or the intuition on what exactly a vector is and the various variations of what a vector is or interpretations is important before you guys start digging into courses such as queerology and queermatics, right? So and also especially when it comes to quantum mechanics or trap mechanics, where we use wave states, and wave states are represented through vector quantities and sort of vector functions or vector valued functions, right? Um, and so that's what it's important for me to give you guys a good explanation of what a vector is before you guys sort of jump in there, or sort of to give any newcomers to the channel a good place to start when studying vectors and linear algebra in general. And when you typically take a linear algebra course, the first thing that you guys are probably gonna be taught are vectors. That's me at least. When I was first introduced to the course, or when I first started studying the course, the first and most fundamental thing that I encountered was the vector. And there are actually many interpretations of what vectors are. And there are four main interpretations. They're listed right here and to the side. But the first interpretation is that a vector to a physicist is an arrow in space and time, which possesses a length, you know, how wide it is or how tall it is if you were to make it stand on top of a plane, and it has an angle. So it has a length and a direction. And there's a third quantity called a sense, because that's what I sort of saw in my calculus textbook. A vector is a mathematical object describing or that has direction, a magnitude, and a sense. And the second interpretation is that arrows can be thought of as elements or objects, like literal objects themselves. Think of them as some abstract, formless objects that are part of a vector space. And vector spaces are sets of vectors. That's all you need to know about vector spaces. A vector space is just a set of vectors. And that's actually a good way, or that's how a majority of us pure mathematicians or people who study pure mathematics talk about vectors, or things we do to vectors, especially linear transformations and matrices. We describe these linear transformations as maps between one vector space and another. And this is actually a very good way or good place to start when you guys are beginning to learn about tensors. Because tensors are not some physical object, but they are something that maps multiple vector spaces onto one vector space. Right. So, pushing aside tensors, that's for another video. Vectors as elements of a vector space. So, as I said, think of them as an abstract object that you can't hold or think or envision, and think of them as part of a set that contains a lot of them, or maybe an infinite amount of them. It could be finite, it could be an infinite field of vectors. And yeah, that's a second interpretation. So this is actually the most fundamental one, and the arguably the most important interpretation of it. In fact, this is how it is introduced to students. They are said to be an element of a vector space, which so happens to have a nice representation as an arrow, which has a direction and a magnitude. Direction, magnitude, and direction and a magnitude. So it's neatly expressed as an arrow in space. And so yeah, that's the second one. The third one is that these guys, okay, think of them again as abstract objects, right? Objects that have no form. Don't think of them as arrows, but instead as objects that we can add, subtract, and multiply, actually, and divide. Actually, when we come to think of addition and multiplication, addition, subtraction, multiplication, and division, we can actually think of this and this as inverses. So as I stated in my orbits video or group video, once you start getting to pure mathematics, it's important to shift your perspective and think that there are merely two fundamental operations in the entirety of mathematics, and that is plus and multiply. Because division is just the same as multiplying a number by a multiplicative inverse of another number. So we can rewrite a divided by b as simply a times 1 over b, which is the multiplicative inverse or reciprocal of b. And likewise, we can write a minus b as a plus the negative form of b. So if these guys are integers, if a and b are integers, subtracting them is just the same as adding 1 to the negative version of the other integer. So it's important to shift your perspective and think that, well, we can, yes, there are 4 really fundamental arithmetic operations, including the square root, but 2 of them can be expressed as a unique, or actually a version of the other 2 operations. So think of vectors as things that we can add, subtract, multiply, and divide by. So that's the third one. And the fourth one is, it requires a bit more explanation, but I'll give it straight to you guys. So when we have a vector space, so suppose we have a vector space, and you can envision that vector space as a grid, right? You can envision a vector space as a grid, or as a plane, a Cartesian or a coordinate system. And when we make the grid, we know that it's like this and it goes like this. So there's lines running perpendicular to the y-axis, to the x-axis, and there are lines that goes perpendicular to the y-axis. How do we know the spacing between each guys for a linear transformation? And that is packaged in the form of a matrix. And the basis vectors. That's why they're called basis vectors. The basis vectors are called what they are because they determine what the system looks like, or the grid looks like, the thing we're working at. They're telling us what the vector space looks like. And in the most conventional, or in the most general case, or the most basic case, I hat and j hat, these two vector identity vectors or basis vectors are just of unit 1, but they point in perpendicular directions. And to change the basis vectors of a system, we simply apply a linear transformation on the vector space, and that is packaged via a matrix. Now, when we think of a vector, it's really nice. It's a very intuitive way to think of them as scalars to the basis vectors of the system. So if we have I hat and j hat, we can express a vector v to be the scalar. So it's going to scale I hat, and we're going to add that result to it scaling j hat. And it checks out because I hat, at least in the most general sense or in the most basic sense, is 1, 0, and j hat is 0, 1. And this array just tells us where the tip of the arrow ends at. So this is the x coordinate and this is the y coordinate. So this tells us that I hat points to the right, only stepping 1 unit to the right, and it doesn't go up or down. And j hat tells us the opposite. So it doesn't step to the right, but it steps upward for 1 unit. And what we can do is express any vector as a scalar to these guys. So if vector v is composed of the coordinates a, b, we can express this vector as a times I hat plus b times j hat. Because when we multiply two vectors, it's just simply gonna yield us, we're just going to multiply the two x and y coordinates. And when we multiply vector v with the corresponding basis vectors, we get 0 on the 0 here. Get it? Because if we multiply AB to 1, 0, we get A, 0. We just add that by B times 0, 1. And that's just, well, that's B. And then we just add the two results, and we get the vector V, AB, which checks out. And yeah, that's the fourth interpretation of vectors. And that is via scalars of the basis vectors of your system. And I think that's pretty much it that I have to discuss about vectors. They're a really trivial mathematical object when it comes to these topics, but they're arguably the most fundamental concept or most fundamental mathematical object in linear algebra. And really, it's an important prerequisite to when you're gonna study matrices, because matrices change these guys, or change the set that contain all these guys. So I believe that's it for the vectors and what they are. First, just to re-summarize it, the first interpretation of a vector is that they are arrows, or they actually I'll start with the most fundamental one. So they are elements of a vector field. So they are abstract objects that are part of a set of, well, all of them in our case. And they are, the second one is that they are addable, subtractable, dividable, and scalable mathematical objects. We can scale them by any other vector, or we can scale them with a scalar or number, and we get a vector. And yeah, the reason why it's called a vector space is because it's closed. It follows certain axioms of what a vector space must follow, and that includes closeness. And that closeness means that whenever, or closeness under an operation, and that means if we ever apply an operation between two vectors, like let's say we're gonna add two vectors. Let's add vector v here with another vector c, d. We get vector a plus c, b plus d. And this vector will be part of the vector space as well. Note that this is just one, this is a vector. It doesn't, even though it kind of looks like a matrix, it's a vector. And this is part of the vector space as well. And so yeah, scalable. And the third one is that they can be scalars, or interpreted as scalars of the basis vectors. So we can scale the basis vectors by these guys and get the same thing anyway. So it's a nice and neat way to express these guys in terms of the reference for what our system looks like. And so the last one, and arguably the most common way people think of vectors, as arrows, or things, or as the villain from Despicable Me would say it, is something that is a mathematical object that demonstrates, or that has a direction and magnitude. Oh yeah! So yeah, that's it for the vector. And next one, I think I'm gonna be doing a video on proofs. And yeah, I'm actually sorry if I'm not able to pump out these videos in a fast way, because I'm currently working on a maths theory. It's an abstract math theory wherein I try to codify math, human stuff, human behavior and stuff. And the concept of vectors and vector spaces are actually going to be pretty crucial there. And I need you guys to understand what a vector is before I begin discussing or codifying human characteristics as vector quantities, or thinking, in terms of vectors. Because that's going to be a really important thing, or a very common thing in our course, in representing human traits and characteristics. And if there's anything that LOSC is known for, it's known for quantifying human behavior and quantifying human characteristics and stuff, sexuality, gender identity, you name it, we're gonna quantify it. And so that's that. And we're also gonna study them rigorously in the lens of mathematics and physics. Not so much as psychology, but we will consult psychologists when it comes to our results. So that's it for this video on vectors. So yeah, reason why I'm not going to be pumping out a lot of videos is because I'm working on a math theory. Please check out my Femboy Mathematics channel so that you guys will know what's up or what exactly it is I'm working on. So that's it for this video. See ya.